This is part one of chapter seven of modern communications, where we discuss dispersive channels and estimate those channels and also develop adaptive equalizer or adaptive filtering techniques uh, to to mitigate the effects of dispersive channels. And then later on, we'll talk about OFDM in part two. All right. So if you think about where we are in terms of sort of our block diagram of the radio system, there's some this discussion of modulation that'll become more important when we talk about OFDM. But we're gonna assume we have some training. We're gonna potentially do some sort of filtering on the receive side, which will hopefully address the issues of associated with dispersion, also involving training and so we'll go through all that and talk about how that works. All right. So given that we have the problem of dispersion, we'll talk about what that means in a moment. Um, we have a couple choices of trying to figure out how to deal with that. One is we can modify our modulation so we can make it easier to work with, or we can try to build an adaptive equalizer, which will just directly compensate for the effects of the dispersive channel. All right. So if we think about what the dispersive channel is, the idea of a dispersive channel is that we have some delay spread or multipath. These are basically the RF versions of echoes. And in particular, the concern is that when you have these echoes in the channel, and sort of like in the cartoon you see in the lower left, it's possible that the signal is basically comes through, and then there's another more delayed signal, and a more delayed signal, and it produces what we call inter-symbol interference. That is, your current symbol has to deal with echoes of previous symbols, and that can make it very difficult to figure out what's going on. Causes potentially make it very difficult to actually figure out what the current symbol is. And this is particularly true because often we would just assume that we could just turn up the power of our signal, and that would improve the signal to noise ratio. And that while that's still true, our signal is now all messed up. And so we just now have a louder messed up signal. Then if you turn up the signal power, you also are turning up that interference as well. So you need a different kind of mitigation approach. So maybe being a little more technically precise, if we think about what a line of sight signal looks like. So here, really line of sight, it's not bouncing off of anything. Um, there, of course, is our signal delayed, by the potentially the speed of light, getting from one point to another. But there are no echoes there, right? There's just one fixed delay. And assuming that we can sync up to it properly, basically it just means that there is some complex coefficient, a single complex coefficient, and at least if we look at it, complex baseband, and that is flat over frequency up to whatever the phase rotation is caused by the delay. So we refer to that as flat fading. But if we have this multiple delays showing up, that is effectively a random filter, right? There is a complex coefficient associated with various delays. And that means we have a frequency selective channel. And so it takes our signal, and we can think of it in the time domain as causing intersymbol interference. We can think of it as the frequency domain as you see in the lower right there, of it having some weird frequency structure that it imposes upon our signal, which causes it to distort in a way that makes it difficult to understand what's going on. So both views are correct. There's a time domain view and the frequency domain view. And basically it causes problems for our signal. So in the lower right, we actually have some examples of channel measurements. So this was measured, it was transmitted from Boston, signals transmitted from Boston and received in Cambridge, um, a bit more than a kilometer long link. It's a couple kilometer link. And what we um, what we see here is at an array of antennas, we estimated the channel. You can think of this as an impulse response, as if there was a single pulse, and we're measuring it. Although technically, this was actually measured using a channel estimation technique, which we'll allude to or we'll go over in a couple minutes. So there's a couple things we can see from this. One is that this this channel impulse response that we see here. Well, first of all, this is just the magnitude of it. We're not showing the phase, but the channel impulse response um, has a delay structure, which means we are seeing these echoes. In particular, um, usually it's big in the beginning and then kind of falls off, which is what you would sort of expect. Um, the signal that we used in this case was had a bandwidth which was a little bit over a megahertz, which means it has a temporal resolution of one over that, which is slightly less than a microsecond. And so you can see the sort of the width of these lobes is on the order of a microsecond wide. These antennas, so there's a single source, but multiple antennas. These antennas are a couple meters apart. Each one is a couple meters apart from the next one. And so it's somewhat surprising that the channel response is so different from antenna to antenna. And a couple things we can take from this. One is that um, well, you can see the separate lobes that are sort of more than a microsecond apart. That indicates that there are distinct paths. Um, and those path differences must be, something on the order of a microsecond. So we can quickly sort of visualize what this means. A microsecond is a thousand nanoseconds, and light traverses about a foot in a nanosecond. And so that means that there are paths that are 1,000 feet, a couple thousand feet different. There's additional paths that are more than 1,000 feet longer, path bouncing around things before it gets to the receiver. So that's interesting. The other thing that we see here is that there's a wild fluctuation from antenna to antenna, even though they're a very short distance apart. And so what that indicates is that uh, the the signal is at some given relative delay actually has multiple paths coming into it. Now we can't resolve it in time, but they will have different phases and multiple paths coming in for each sort of approximate point in time. So you can imagine that, yeah, there are some signals that are delayed by a few thousand feet. Um, but there are other signals that maybe are just delayed by several feet. And so you can't actually see that relative delay. It's not long enough for us to actually notice it. But it is some number of wavelengths different. And when so two signals coming in with multiple wavelengths, they're sort of potentially wavelengths different, they add up coherently at a given delay. And if it were, say, four wavelengths excess delay, get it from two different paths coming into a given antenna, well, those signals will combine coherently and they will just make a larger return. But if it were, say, 4.5 wavelengths difference in the length, then what happens is they add in the at complex baseband point of view out of phase, and so they combine destructively and will make it smaller. So there's a lot of multipath coming in. That's what this looks like. And in fact, it's pretty complicated and even more complicated than you see based on just the structure and time. Another piece to this is that it does vary a lot from antenna to antenna. And this explains why you often see at, say, the base stations, multiple antennas that are some distance apart from each other. And what they're exploiting and to improve the signaling going to the base station is diversity. So by having diversity in antennas and multiple antennas at slightly different positions, what you end up seeing is that the same signal coming in because of just some complicated set of paths coming in will be stronger than at one antenna compared to another antenna just a little small distance away. And we see that here explicitly, say, comparing antenna 2 to antenna 9. The signal coming in at antenna 2 is huge compared to antenna 9, even though they're not actually that far apart. This is the result of that destructive versus constructive combining of signals that are coming in. And as a consequence, if you have this sort of diversity, you can pick the better antenna and get noticeable improvements in terms of the signal noise ratio at the receiver. In any case, I think these experimental results showed that it can be relatively complicated. All right. So in the upper right, you see the equation for a continuous version of the channel impulse response convolved with our transmitted signal showing up the receiver, and then of course in the receiver you add some more noise. This is the integral form. We could also write down in sort of the simpler convolution form. That is the channels convolving with the transmitted signal. Of course, when we do this in our computer, we sample things in time, and so we can think about the channel and the transmitted sequence and being sampled in time. In which case, our convolution then ends up being a sampled convolution, and we can represent that in terms of a vector matrix multiply. So if we take our signal, and there's a typo here. This shouldn't be an S. It should be an X here. Anyways, so if our S is made up of a bunch of transmitted X's, each off at a one sample delay, two sample delays for the third row, four sample delays, for later row, so forth. Then H has a complex coefficient associated with each delay. So first row, no delay, second row, one delay, third row, two delays, so forth. And then they get added up when you do this vector matrix multiply. So it's not particularly important, but we often sort of grab the first number of samples because what happens is when you do this convolution, the length of the output of the convolution is the sum of the lengths of the two vectors minus one. And often, just for the sake of convenience, we want to produce an output that is the same length as the transmitted sequence. May not be important, or often it's not important, but it will help us think about this a little bit. All right. So let's say we want to estimate what this channel is. Now, this doesn't fix it for us. We're just trying to figure out what's going on. One thing we would like to do is to build a good estimator. And so to do that, we might consider using a maximum likelihood estimator. So first of all, I'm going to build a new vector x sub h, which is basically taking the first n sub s samples of convolution of our sampled channel impulse response, and the transmitted sequence x. We're going to assume the portion of the transmitted sequence that we're looking at is the training portion. That is, it's a set of known symbols that are being sent, so the transmitter and receiver agreed on these training symbols beforehand, and we're going to use that to estimate h. So what we see up here is the probability density function for a sequence of symbols being transmitted that have been convolved with the channel. We're going to assume, and for this form, that the noise being added is independent from sample to sample and that it's complex. So we have complex baseband sort of sensibility here. We have complex noise, that's circularly symmetric Gaussian noise, But we're dealing with the whole vectors, so this is the multivariant version of that noise, where it's independent from sample to sample. All right. Now we're going to use this probability density function in a slightly strange way to get the maximum likelihood estimator. What we're going to do is we know and buried in this thing is h. We're going to find an h which maximizes the likelihood given that we know x and that we observed z. So usually we think of a probability density function as sort of where h and x and the variance are all of the variance of the noise are all inputs, and then z is an output in some sense. But we're going to try to turn around. We're going to make z an input, and we're going to try to optimize the likelihood to be maximized to find a good estimate of h. All right. So naively, what you might go is like, all right, I'm going to put my observed value for z in here, and I know x. I could then just start trying different values of h to maximize that likelihood, and that does work. But it's fortunate in this particular case we can actually come up with a clear functional solution. So to do that, you might naively go, well, I'll just take the derivative with respect to h. Well, it's a little problematic because h is a vector, but you can do that. You can take the derivative with respect to vectors. But a more complicated problem is that h is a vector of complex. So it's a complex set of parameters, or a vector of complex parameters. And taking derivatives of that is not well defined. So we're going to do that trick we've discussed before. And we're going to say h is a function of some real parameter. So the probability density function, while it has a bunch of complex stuff in it, is real, and alpha is real. So we can take the derivative with respect to the probability density function, with respect to alpha, and it's all well behaved. We can make our life a little bit easier by recognizing that I could, instead of directly doing this, it would work, but it's slightly easier if I think about the log-based e of the probability density function. So it's a monotonic function, and so whatever maximizes whatever maximizes the likelihood, whatever h maximizes the likelihood, that will also maximize the log-based e of the probability density function. And this is just a trick to make our life a little bit easier. So when I take the log-based e of the product of these constants and e to something, what I get is the log of the constants plus the log of e raised to the exponent. Well, if I can just take the log of the constant, I'll call that k for the moment. And then when I multiply that times this, take the log, it ends up being a sum. So then the log-based e of e to something is just the exponent. And so what I get is just the exponents out. So I have negative z minus xh times z minus xh Hermitian conjugate divided by sigma squared, right? So it's just basically the exponent is left over. When I take the derivative with respect to alpha, well, k has no alpha in it, so it's going to go away. I'm going to set this thing equal to 0 anyway, so I can multiply both sides by sigma squared, and that goes away. So I'm just left with basically the quadratic form of z minus xh times z minus xh Hermitian conjugate. All right, so when I take the derivative, I got to do the chain rule. That is, I take the derivative with respect to the first term, multiply the second term, and then I have the first term times the derivative of the second term. Because it's a real function, and I'm going to take the derivative with respect to real function, derivative of real function with respect to real parameter, the thing has to be real. The output of the derivative has to be real. So that means if I get the two terms out of this quadratic form, those two terms have to be the complex conjugate of each other. All right, so what we can do basically then is only worry about the one term. If we can set that to 0, then both terms are going to go to 0. All right, So I'm going to focus on the sort of the second term from the chain rule. That is, I'm going to have the first term, z minus xh. Recall that xh is basically the h times the capital X, which is the transmitted sequence and delayed version of the transmitted sequence of the training data. Um, and then I got to take the Hermitian conjugate of the second term and then take the derivative with respect to alpha. So that will flip the order of x and h. So then I get an x Hermitian, and then I get the derivative of h Hermitian with respect to alpha. Now, we never defined what that relationship was between h and alpha. We just said h is some function of alpha. And we never will actually define it. What we're going to say is if I can get the first term, the term multiplying the derivative of h Hermitian conjugate with respect to alpha, get that first term set it to zero, then everything's going to go to zero. So what I can do then is I can say, well, by setting that to zero, I go z times h Hermitian minus h times x times x Hermitian. And I can move the h times x Hermitian to the other side, then multiply on the right-hand side everything by x Hermitian matrix inverse, and that'll get rid of the x Hermitian that's multiplying the h, and it's kind of we leave it over on the right-hand side. So what we get then is an estimator. That's what we have a little hat on the h. It's equal to the observed training symbols times times x, which is the transmitted training symbols and a bunch of delayed versions of that, times the matrix inverse of x Hermitian. And it turns out this is the least squares estimator. So we started off trying to get the maximum likelihood estimator, and it turns out it generates a least squares estimator for what it's worth. The first part of this estimator, the z times x Hermitian, basically is a cross correlation, if you like, between the observed sequence of training data and the transmitted sequence and a bunch of delayed versions of that. And the x Hermitian is basically an autocovariance estimate or proportional to an autocovariance estimate. And so there's some structure here that in some sense makes sense. Anyway, so we now have an estimate of the channel is, and that can be useful, but it's not exactly what we want. We actually want to mitigate the effects of it. But at least now we understand what's going on if we use this. All right, so now what we're going to do is we're going to build an adaptive filter to not just understand what's going on with the environment, but actually to fix, to some extent, the effects of that dispersion. All right, so what we're going to do is we're going to build a filter, and we're going to build a filter such that some set of complex coefficient multiplied by the received signal at various delays. So there's a complex coefficient associated with each delay, and you add those together as a function of time, and that will give us some estimate of what was transmitted to S. However, we might build a good filter, we might build a bad filter. If we do a good job, then the difference between them is small in some sense. When we do a bad job, the difference between them is big. And that difference is basically the error. And so what we'd like to do is get the expected value of the mean squared error and as our expected value of the squared error. We'd like to drive that down to zero, or we can't go to zero, but we'd like to make that as small as possible. All right. And so that's the sometimes referred to as the Wiener filter. Now we can do this all in an asymptotic sense, but I'm going to skip that and focus on a sampled version because this is what we really do. We basically have sort of in our processor sample data, and we do everything in this sampled space. So let's focus on that here. So I have a model. There's some channel that lives in H, and it's a bunch of complex samples as a function of delay. We have training data, which lives in T, which is basically the training data that's transmitted and the various delays of it. And of course, we add some complex Gaussian noise to it as well at the complex baseband. We're going to build a filter. So this is going to be our approximation to the Wiener filter based on these finite samples. And so those filter coefficients live in W. And we're going to build a data matrix Z, which basically has our received signal and then a bunch of delayed versions of the received signal. And so when we take W Hermitian times, so W is a column vector, when we take W Hermitian times Z, it's basically going to multiply each delay by some complex number and add those weighted, complex weighted delayed signals together, and that'll give me uh, an estimate of the training data of sent. So if we do a good job, the estimate of the training data is going to be close, and if we do a bad job, it won't be close at all. And so what we have is an error vector, which is the difference between the output of our filter versus what we know truth is. And so W Hermitian times is stacked up and delayed T is Z minus T is basically that error. And so what we want to do is um, take a look at the sort of our estimate of the mean squared error. So I can take the L2 norm of the error vector and divide it by the number of samples, and that's a good estimate of the mean squared error. I'm going to assume that W is a function of alpha, right? Same trick we played just a second ago. And so what I'm going to do is take the derivative with respect to alpha. And so when I take the derivative with respect to alpha, I have a form of the error. I can throw away the n sub s because it's going to set it to zero anyways. And so I can multiply both sides by n sub s, doesn't anything. But the squared error ends up being the error times the Hermitian conjugate of the error. And so that's WHZ minus T times quantity WHZ minus T Hermitian. And so now once again, I take the derivative with respect to alpha. And I have to do the chain rule once again because this is a real derivative with respect to a real valued parameter. That is the L2 norm squared. The result has to be real. And since it's made up of a bunch of complex stuff, that means we have to have two complex things that added together becomes real, which means some terms are added to the complex conjugate of those terms. Because of that, we can basically say if we can get one of the terms to go to zero, the other term, the complex conjugate of zero, is also zero. All right. So once again, doing the chain rule, we can take the derivative of W with respect to W Hermitian with respect to alpha, and that will then leave us with a Z. So we get the derivative of W. Z doesn't have any alphas in it, but it's multiplied by the W, so it survives. T doesn't have alpha in it, so it goes away, and then we multiply it by the second term. And then, of course, by the chain rule, there's also the other term as well. But we don't have to worry about it because if we can set this term to zero, then we have solved our problem. All right, so what we're going to do is set it to zero. I can multiply the Z out, and so then I get Z Hermitian times W is equal to Z times the training data Hermitian. And then I can multiply both sides by the matrix inverse of Z Hermitian. And that gives me an estimate of the filter we want to use to mix them to minimize our estimate of the mean squared error. All right, so let's do an example. What we see here is we have built a some arbitrary channel. You can see that kind of random coefficients associated with various delays. I'll normalize it so that the L2 norm is one. Um, and then, of course, we will take that vector and apply it to our training data and figure out what's going on from there with a bunch of delayed versions of the training data. So that's what the received data is going to look like. Because our channel is represented by a bunch of delayed coefficients, we can take the Z transform of this and then use the trick of Z replacing Z with e to the I 2 pi f and magnitude squared of that, and they'll give us a spectral estimate. If we set that t to 1, then it's a normalized frequency. And so what we see is basically the channel has a spectral response. So the channel explicitly gives us a time delay response. But we can now calculate the spectral response. And what we see is kind of a deep notch here in some shape that flows across the spectrum. Certainly very much not flat. So you can imagine if you're sending out QPSK, it has to go through this channel and it has bad effects. So let's imagine we're sending QPSK signals across, and if we put this in a high signal noise ratio environment, the noise, of course, causes the points to be spread out, and that's what you see in the second plot here. But it's still pretty easy to figure out how to separate the different points in the constellation. If we instead take our QPSK, run it through this channel, and then add noise, what we see is the plot over on the right, and you can see that it's basically uninterpretable. It's a big mess. And so that's our problem. We have to figure out how to deal with that. So we can go through the process. We have some training data. We take a look at that training data and we build the adaptive filter. When you do that, it's always good to look at the coefficients of the adaptive filter. So we got the real and imaginary part of the coefficients. We can see that this is relatively well behaved, and the reason why I know this is that if I have really large values at the edges, that means sometimes it means that the filter is struggling to be well behaved. But this has nice weights in the middle, and so this is a relatively happy filter. Using the same trick, when taking the Z transform and substituting Z with the exponential, we can get the filter shape of the Wiener filter. And so it has some kind of messy shape here. Now we can put it all together. So we have the messy spectral shape of the channel. And then we have the basically our adaptive equalizer, our adaptive filter, which is going to try to compensate for it. So then if we run our signal through the channel and then run through the filter, what we see here is that it gets pretty flat. And there's one little dip here. Now you might naively think that's the result of basically a failure. That is the channel or the adaptive filter didn't fix the channel properly. However, that's actually not right, or that's not the right way to look at this. If you take a look at the original effect of the channel, you notice there's a super deep notch here. And so if our filter brought that notch all the way up, what happens is there was almost no signal left there. There wasn't really much signal left there. And so by bringing that back up, it's actually just blowing up noise in this region. So it kind of doesn't want to do that because it's just adding noise. However, having the notch there distorts the signal too. And so we kind of do want to bring it up. And interestingly, the result is it brings it up, but it doesn't bring it all the way up. So it finds a balance. And it finds the right balance to minimize the estimated mean squared error, which is what we want to do. And so at the output of our adaptive filter, what we see is we recover the QPSK shape. It's not as tightly clustered as a noise only scenario, but then we shouldn't expect it to be because it's trying to solve lots of problems here. And that was kind of a messy channel. But nonetheless, it's dramatically better than what we saw before. All right. So in the next part, we'll talk about in the next recording, we'll talk about other techniques for trying to compensate for the dispersive channel.